Hello friends, I welcome you in lecture number 22 on group theory. In this lecture we will talk about Lagrange theorem. Lagrange theorem is important theorem of group theory. So before going for Lagrange theorem we understand this definition. The number of elements of a group is called the order of the group and it is denoted by this notation. Between two vertical lines we write down capital G. So this is the notation for order of the group, and order of the group means the number of elements in the group. Suppose group has 5 elements, then we will say that order of group G is 5. Now what is Lagrange theorem? So Lagrange theorem is about order of subgroup and order of group. Lagrange theorem says that the order of a subgroup of finite order divides the order of the group, or we can say that if capital H is a subgroup of a finite group G. Finite group means number of elements in group G are finite, that is order of G is finite. If H is a subgroup of a finite group G, then order of H divides order of G. So we are going to prove this theorem, Lagrange theorem, which says that the order of subgroup always divides the order of the group. Now in the proof of Lagrange theorem we are going to use properties of cosets which we have discussed in earlier lectures. So we just recall the properties of cosets which we are going to use in proving Lagrange theorem. So we just recall those properties. Let capital H be a subgroup of a group G under binary operation star, and we will discuss all these properties for left cosets. Same properties are true for right cosets as well. So we know that the left cosets form a partition of group G, that is we can always write G as the union of left cosets, say AH, where A belongs to G, and all these left cosets are either equal or disjoint, so they will form a partition of group G. If we construct this set of all left cosets of a group G, then this set is the set of all left cosets and this set will be a partition of group G. Another property which we have seen is the number of elements in any left coset is equal to the number of elements in the group H. That is, order of left coset AH is equal to order of H for any element A belongs to G. We know this property also. Two left cosets are either equal or disjoint. For example, if I take two elements A1 and A2 in a group G, then either A1H equal to A2H or A1H and A2H are disjoint, that is their intersection is empty set. And we have seen this property also. If A1 is an element of left coset corresponding to A2, then cosets corresponding to A1 and A2 are always equal. So we are going to use these properties in proving Lagrange theorem. Cosets are either equal or disjoint. Similarly, the number of elements in any coset is equal to number of elements in the given subgroup, that is size of left coset. Each left coset is equal to size of the given subgroup, and the left cosets form a partition of G. So using these properties we are going to prove Lagrange theorem. Lagrange theorem says that the order of subgroup always divides the order of the group. That means I have to prove that if H is a subgroup of finite group G, then I have to show that order of H divides order of G, or I have to show that order of G is multiple of order of H. I have to find out some positive integer small n such that order of G is multiple of this order of H, that is n into order of H for some n belongs to n. So we will try to write down order of G as a multiple of order of H. So how to prove this? Order of H divides order of G. So for that we know that this G is a finite group, so the number of elements in G will be finite. So we start by taking any element, any particular element of group G. Let or take A1 belongs to G. Then we know that if we take left coset corresponding to this element, then order of that left coset will be equal to order of given subgroup, which is denoted by capital H. Now suppose this left coset A1H is equal to group G, then we will say that order of A1H equal to order of G, and this implies order of G will be equal to order of H, because order of A1H is equal to order of H. So we have shown this, that order of H and order of G are equal, therefore order of H divides order of G. But if A1H is not equal to G, suppose A1H is different from G, then there exists some element, say A2 in G, such that A2 is not present in A1H. Now because A2 is not present in A1H, left cosets corresponding to A2 and A1 will be disjoint, because we know that left cosets, any two left cosets are either equal or disjoint. Now since A2 is not a member of A1H, A1H and A2H cannot be equal, therefore they must be disjoint. Also we take the union of A1H and A2H, and we find out the number of elements in the union of these two left cosets, and because these two are disjoint, number of elements in A1H union A2H will be equal to addition of order of A1H plus order of A2H, and we know that number of elements in any left coset are equal to order of the given subgroup. So this is equal to order of H, this is equal to order of H, that is 2 times order of H. Now suppose this union, if A1H union A2H equal to G, then order of G will be equal to order of A1H union A2H, and that is nothing but 2 times order of H, and we can see that order of G is integer multiple of order of H, therefore order of H divides order of G. But suppose this is not equal to G, then we consider another element. Suppose A1H union A2H is different from G, then there will be A3 in G, then we take element A3 in G such that A3 is not present in the union A1H union A2H. A3 is absent in A1H union A2H. Now since A3 is not present in the union, that means A3 cannot be in A1H as well as A3 cannot be in A2H, and this implies that A1H and A3H are disjoint as well as A2H and A3H are also disjoint, and we have shown that A1H and A2H are also disjoint. So if we consider these three cosets, three left cosets A1H, A2H, A3H, then they are pairwise disjoint, and if we take their union A1H union A2H union A3H, then order of union will be equal to order of A1H plus order of A2H plus order of A3H, because all these are pairwise disjoint. Now this is equal to order of H, because all the left cosets are having same order as order of given subgroup. So this is equal to 3 times order of H. Now if this union is equal to group G, then order of G will be equal to 3 times order of H, and we can see that order of H divides order of G. So we continue this process until the last element of group G. Suppose last element is nth element, suppose there are n elements, then after n number of steps we will obtain that order of A1H union A2H union A3H and so on union ANH will be equal to n times order of H, and this will be equal to group G. So therefore order of G will be equal to n times order of H, and therefore order of H divides order of G. So in this way we can use properties of left cosets to prove this Lagrange theorem. Okay, fine. So I have written that proof systematically here. We want to prove that order of H divides order of G. So our aim is to write order of G as some integer multiple of order of H. So for that we start by taking element A1 in the group G, and we know that order of any left coset is equal to order of given subgroup. So therefore we can write that order of A1H is equal to order of H. Now if this A1H is not equal to G, then we consider another element A2 in G minus A1H, that is we consider A2 such that A2 is element of G but A2 is not an element of A1H. Now because A2 is not an element of A1H, A1H and A2H are different, and we know that two left cosets are either equal or disjoint. Therefore we can write that intersection of A1H and A2H is empty set, and order of union of A1H and A2H will be equal to order of A1H plus order of A2H, because these two are disjoint, and order of A1H is equal to order of H plus order of H. Here we are using the property that order of any left coset will be equal to order of H. So this is equal to 2 times order of H, and if this set union of these two is equal to group G, then order of G will be equal to 2 times order of H, and we have shown that order of H divides order of G. Now suppose this is not equal to G, then we take another element such that that element A3 is present in G but it is not present in this union, and therefore we will have these disjoint sets, because A3 is absent in A1H, A1H and A3H are disjoint. Similarly A3 is not present in A2H, therefore A2H and A3H are disjoint, and we have pairwise disjoint cosets, and therefore order of union of these three left cosets will be equal to order of A1H plus order of A2H plus order of A3H, and order of each left coset is equal to order of H. Therefore we have 3 times order of H. So we continue in this way, and after n step we will have accounted for all of the elements of G, and we will have G equal to union of this say n left cosets A1H, A2H up to so on union A and H, and order of G will be equal to order of A1H plus order of A2H plus order of A3H and so on plus order of A and H, because all these are pairwise disjoint and all the left cosets have the same order as order of H, and this is n times. Therefore order of G equal to n times order of H, and therefore we can say that order of H divides order of G. So here we have used that left cosets of a subgroup H construct a partition of G. Here we can see that partition union of all these left cosets if is group G, and all these left cosets are disjoint, therefore they form a partition of G, and using this fact we are able to prove that order of subgroup divides order of given group. So I hope you understand this proof. We are frequently using these properties of cosets. First property we have used is order of any left coset is equal to order of subgroup H. Another property we are using is any two left cosets are either equal or disjoint. So here A2 is not present in A1H, therefore A2H and A1H are not equal, therefore they must be disjoint because two left cosets are either equal or disjoint. And using that property we are able to write down order of this union as order of A1H plus order of A2H. And finally we are writing G as the union of all these possible left cosets, and we find that order of G equal to n times order of H for some positive integer n, therefore order of H divides order of G. So they can ask you this type of questions. This question was asked in GTU summer 2021 exam for 7 marks, and they have asked the question in this way: explain cosets and Lagrange's theorem. And because it is for 7 marks, you should define what is left coset and right coset, and then you should write the statement of Lagrange theorem, and you should prove this Lagrange theorem in this way. I have shown how to prove Lagrange theorem. So we can consider 2 marks for the definition of coset, or for this we can have 2 marks and 5 marks for the Lagrange's theorem. So sometimes they ask this type of theoretical questions also. So that is the reason why I have proved this Lagrange's theorem, which says that if H is a subgroup of a finite group G, then order of H divides order of G. So remember this statement and proof as well. If you have any doubts, you can ask in comment section. So I stop here. Thanks for watching.